Well, we're going to have a look at general solution of trigonometric equations, an area which is greatly misunderstood. So hopefully we can shed some light on this. Now, general solution of trigonometric equations basically means that we are not specifying the domain where the solution has to reside. So we have to come up with an expression where we're allowing for an infinite number of solutions, because as we know, sine, cos and tan just keep on repeating forever and ever and ever and ever. So we have to basically come up with a representation where every single possibility is covered. And this is actually relatively straightforward to do. Take the example, we've got cos of x equals 0.5 or a half. We think, what's our basic angle in quadrant 1? Yes, I hear you say it's pi on 3. Now, which quadrants apply to a pi on 3 basic angle in quadrant 1 but a positive cos result? Yes, they are quadrants 1 and 4. Okay, so now we've got to come up with a way that represents all the angles in quadrant 1 from the basic angle with 2 pi then added repeatedly till you get to infinity, or backwards to minus infinity, and also quadrant 4 adding 2 pi up to infinity or subtracting 2 pi for revolutions going backwards to infinity from that basic first value that you get. So I've added that in there, the pi on 3 angles, to get some idea of what we're trying to do here. Now, for cos, for positive cos, we usually express the solution as x is plus or minus pi on 3, because that encapsulates both those solutions that I've just showed you there on the cast diagram, plus 2k pi, where k is an element of z, meaning any integer. And I've written in red, please don't omit this, because that is completely incorrect if you omit it. You have to state what k is. If you go just inventing a symbol for k, you have to state what k means. But the beautiful part about this way of expressing our solution is that we have covered every possibility, because k can be negative, any negative value, k can be any positive integer value, and it can be 0 as well. And if you start plugging in some values of k, you will see how beautifully this caters for the infinite number of solutions that this gives us. Alright, now we're going to look at root 3 tan of 3x equals 1. Okay, let's see now, what are we going to do with that? Yeah, tan of 3x equals 1 over root 3. The basic angle in quadrant 1 is pi over 6. And hence now, with tan, we can say that therefore, because tan has a period of pi, we can say that our 3x would be pi on 6 plus k pi, not 2k pi, like you see above for that cos example, but k pi, because tan has a period of just pi. It's easy as pi, isn't it? I just thought of that. Sorry about that. Okay, you must put in there that k is an element of z. But of course, that'll allow for every single negative value of k, for 0 for k, and for positive values of k, and we've captured everything. But of course, that's not the end of the story with tan. We've got to find out what x is, not what 3x is. So let's just, there we go, yeah, z can be negative or 0 or positive. So into column 2, and we've divided by 3, and I've given you the final Alakazam answer, and there it is for you. Okay, that covers it. Now, don't get all hung up about how you represent these things in the way that maybe the textbook represents them, because the textbook can represent them differently. For example, if you took that first example of cos of x is, say for example you said it was minus a half, then you'd be looking at quadrants 2 and 3. And in that instance, you'd have to come up with a way of representing all the angles in quadrant 2, and, as well as that, all the angles in quadrant 3. And that would be a different way than you can see there for that example where cos of x was positive 0.5. Okay, so the only way you can really figure out whether you've got it right is basically test your answers and see whether they're working, and against what some other representation might be, and check that they're actually the same. Alright, another one. 2 sine of 2x equals root 2. Okay, let's just get rid of that 2, divide both sides by 2. So sine of 2x equals root 2 on 2. And that's looking familiar. The basic angle for that one is pi on 4. Yes, it is. So now we've got to figure out which quadrants our solutions are going to be in. And yes, they are. They're in quadrant 1 and quadrant 2. So we've got to find a way of representing the infinite number of solutions for this example. Now what I do is I just have a separate expression for the quadrant 1 equivalence and the quadrant 2 equivalence. So what I say is for quadrant 1 we've got 2x equals pi on 4 plus any number of revolutions forwards or backwards from that, and that gets us, dividing by 2, you get x is pi over 8 plus k pi, where k is an integer. Don't forget that k equals an integer, because you're going to be wrong if you do. So, for quadrant 2, we can say that, of course, 2x equals 3/4 of pi plus any number of full revolutions forwards or backwards. Then we just divide by 2, and we get, x is 3 pi over 8 plus k pi. Now, please remember to divide the k term as well. A lot of students forget to do that, and it's just not right. So that's my solution to that particular example. Lovely. But the thing is, if you do that example and you look up the textbook might say what looks to be something different, and you might think, oh, I've got it wrong, but you probably haven't got it wrong. So I'm just going to kind of let you into that secret. The answer may be in a different form when you're looking up the textbook. Looking not the same, but it probably is the same. And what you have to do is test yours against the solution by substituting specific values of k, or whatever the variable you've put in there to account for the infinite number of revolutions. Okay, now I'm just going to give you, I'm going to magically make that left-hand column disappear. Oh, look at that. Beautiful. And now we're going to show you a couple of different ways of representing that that solution there with the blue box around it. Okay, so for that solution, let's just see what else they might say. Alternative examples or expressions for the solution include, I've put down 2 of them. Let's have a look. Here's the first one. That looks completely different, but actually it's the same. All they've done there is they've put both terms in the solution under the same lowest common multiple of 8. And it looks kind of like weird and different, but it's not different at all. It's exactly the same. And if you don't believe me, start plugging in some values of k and see if between the 2 different ways of representing the solution, and they will be the same. They will be the same. Now this second one is pretty crazy. Ooh, look at that. My goodness. What did they do to that? Well, when I look at that, I think that is just, what planet did that come from? And then I think, look, the only way I can figure that out is basically just to plug in some values of n in that instance and see if they kind of work out. And if you do that, you will see that it does work. So I've just expressed what I just said previously, that 1 is just the same, solution 1 is the same except it's over the LCM, and 2, big problem. But as I said, try different values of n and verify that it is the same. And it is. Yay, it is. So I don't think that you'll need to worry about expressing sign solutions, general solutions, in that second form, and I wouldn't worry about it. However, you might have to unravel some multiple choice options in the multiple choice sections of the examinations, and they might put the answers in that form, in which case you have to keep your head, take a deep breath, and basically just plug some values of n into that and see whether they work. Okay, that's the way to do it. So you watch for the type 2 expressions of the solutions for sign, maybe in the exam multiple choice section. Other than that, I wouldn't even worry about it because I don't think it's important. What is written on the right hand side in the blue box is perfectly valid. It's a perfectly valid solution. So there you have it. I think general solutions are probably easier, really, as far as I'm concerned, than the ones where you have a restricted domain, because you don't have to fiddle-faddle around trying to work out all the different things that are in range and out of range and all the rest of it, which, gets a bit tedious after a while. This stuff is really easy, but the big danger is students either leave out the k as an element of z, or when they're dividing, to say from a 2x solution down to x, they just forget to divide both terms, the actual basic angle term and then the 2k pi or the k pi term in the case of tan, and then they get it wrong. And it's just absolutely so widespread. So I just want to rant a little bit and tell you, please be careful. It's really easy. Alright, thank you so much for listening. There's the general solution stuff, and we'll see you later.